Hi class. In the last video where I introduced the idea of asymptotic expansions, I mentioned that one of the situations in which asymptotic expansions arise is at an irregular singular point of an equation. I wanted to give you an example of that. This example is actually taken from Bender and Orzag. You can find it on pages 77 and 78. And here's the ordinary differential equation we're considering. X cubed y double prime equals y. That is, the second derivative of y minus 1 over x cubed y equals 0. In the notation I introduced last time, this coefficient b of the most general second-order ordinary differential linear differential equation is 1 over x cubed, or minus 1 over x cubed. The limit as x goes to 0 of x squared times b of x diverges. Therefore, x equals 0 is an irregular singular point. We can see that we can't get a series solution around x equals 0 by just trying it. Suppose we try, basically this is a Frobenius solution, essentially a Taylor expansion or a power series in n, where we allow the power to be an arbitrary, to differ by integers, but be offset by some arbitrary constant alpha, which could be a fraction or even irrational. If we plug this in, assuming that the series expansion converges, taking two derivatives, I get a power of n plus alpha minus 1 of an x to the n plus alpha plus 1 once I multiply by x cubed. I'm rewriting that form of the equation. And on the right-hand side, y, I just get some n going from 0 to infinity an x to the n plus alpha. Now, if you think about this for a minute, you see that we immediately have a problem, because on the right-hand side, the power series starts with the powers of x to the alpha. On the left-hand side, it starts with powers of x to the alpha plus 1. So immediately that tells us a0 equals 0. But actually, given the form that we started with, we can shift the expansion by changing what we mean by alpha. So this only is meaningful if a0 is not equal to 0. So this is a contradiction. There is no solution of this form. So it turns out, though, we can still analyze the behavior of the solution. And the way we do it is to try looking for a solution of the form y of x equals e to the s of x, where s is a function. We've rewritten the function y as the exponential of a different function. And what we'll see is we're going to get an expansion. I'm going to assume x is positive. You'll see why in a moment. This is going to be an expansion, which is an asymptotic expansion, which is valid as x goes to 0 from the positive side. The derivative of y prime is s prime e to the s. If I take y double prime, I get s double prime plus s prime squared, quantity times e to the s. If I plug this into the equation, I find that s double prime plus s prime squared is 1 over x cubed. At this point, I haven't made any approximations at all. This is an exact expression. I've traded what was a second-order linear differential equation, however, for a second-order, actually it's essentially a first-order nonlinear differential equation. Now, I'm going to try to find an asymptotic expansion, a series solution of the form, so I should write this with a tilde sign. I'm going to try to find an asymptotic expansion, S, of the form S0 plus S1 plus higher order, such that in the limit x goes to 0 plus, S1 over S0 is 0. So this, in the limit x goes to 0 plus, S1 is a smaller term than S0. Presumably there would be an S2 and an S3, each of which would be subsequently smaller. At 0th order, if I just plug in S0 into my expression, I'm going to get S0 double prime plus S0 prime squared is asymptotic to 1 over x cubed. I write asymptotic here because this isn't an exact expression. I just want to capture the leading divergent behavior as x goes to 0 from the positive side. Well, the question that confronts us is which of these terms, S0 double prime or S0 prime squared, is likely to be larger. With experience, you will see that especially in the case of an irregular singular point, it's generally the square of the first order term that's larger, and we'll see that directly in a moment. Let's assume that S0 double prime is much less than S0 prime squared. So in that case, S0 prime squared is asymptotic to 1 over x cubed. S0 prime is proportional to plus or minus 1 over x to the 3 halves. So S0 is plus or minus 2 x to the minus 1 half. Now, we can already see, looking at this equation, why we would expect S0 double prime to be smaller than S0 prime. That's because if this dominant balance says S0 prime is 1 over x to the 3 halves, S0 double prime is going to be 1 over x to the 5 halves, as we see here. And so the limit as x goes to 0 from the positive side of the second derivative over the square of the first derivative is proportional to the limit as x goes to 0 from the positive side of x to the minus 5 halves over x cubed, and that is equal, x to the minus 3, excuse me, s0 prime goes like x to the minus 3. So that actually does go to 0. So our assumption that s0 double prime was much less than s0 prime squared and s0 prime squared was the dominant term that we need to account for in constructing an asymptotic series, is self-consistent. So let's go to next order. Let's take our initial asymptotic form, plus or minus 2x to the minus 1/2, and see if we can find the form of s1. Well, s double prime is equal to, s double prime we just calculated is equal to plus or minus 3/2 x to the minus 5/2 plus s1 double prime. And s prime then is minus or plus x to the minus 3/2 plus x1 prime. So if I plug this into the expression, I get, if I look at the second derivative, I'm going to assume that this term is bigger than this term. So the s double prime term gives me s0 double prime plus or minus 3/2 x to the minus 5/2. I have s0 prime plus s1 prime squared, and that whole thing has to be equal to 1 over x cubed. That's my original equation. This comes from s double prime plus s prime squared equals 1 over x cubed. That was the form of the equation I'm trying to solve. The 1 over x cubes cancel as they must, and now I have potentially three terms. I have the s0 double prime term, which is this term. I have the cross term, which I've written here, minus 2x to the minus 3/2 s1 prime, and I have s1 prime squared. We're going to show that what balances in this case is the first term, s0 double prime, with the cross term, 2s0 prime s1 prime, and that's going to be much bigger than this last term, s1 prime squared, where again bigger means in the limit where x goes to 0 from the positive side. If I assume these two balance, by solving this equation, I get s1 prime is plus 3 over 4x, so s1 is plus 3/4 of log x. Now I need to check that s1 is really smaller than s0 in this limit as x goes to 0 from the positive side. That's the limit as x goes to 0 from the positive side of log x over 1 over x to the 1/2. That's equal to 0. I also need to check that this term I assumed was small, s1 prime squared, is less than the term I kept, 2x to the minus 3/2 times s1 prime. 1 s1 prime cancels. I therefore get the limit of 1 over x, because s1 is just proportional to log x, its derivative is proportional to 1 over x, and 1 over x to the minus 3/2. And you see as x goes to 0 from the positive side, that's also 0. So everything's consistent. I have an expansion then that says y is asymptotic to e to the s0 plus s1. s0 is plus or minus 2x to the minus 1/2 plus 3/4 log x plus a constant. So overall, the behavior in the limit x goes to 0 from the positive side to the solutions of this differential equation are proportional to x to the minus 3/4 times e to the plus or minus 2x to the minus 1/2. This is just the start of an asymptotic expansion. I could have an s2 and s3, and you should think about what I expect for the next term. If you look at this expression here, this term started with an x to the minus 1/2. The next term, this is like log x is like x to the 0, so we might expect the next term is likely to go like x to the 1/2, and the term after that to go like x, etc. You should also think about what would be different if I had let x go to 0 from the negative side. What would the dominant expression be like for the solutions on that side? So this was an example. You'll have other examples in the homework, but this was an example of finding an asymptotic expression for the behavior of differential equation around an irregular singular point. And the basic method was to try a solution with form y equals e to the s, and then obtain an asymptotic expansion for s.